So implicit differentiation is related to related rates, which is why we put them together. And just to be clear, this is what we're doing on this page. And then the next page is related rates. So this entire first page is implicit differentiation. And it's the kind of thing that we already know how to do, but the notation and the interpretation sometimes can be a little bit tricky. And so that's what I really want to focus on this page. And then we're going to apply this concept on the next page in really interesting ways. And so this is another kind of culmination, in my opinion, the optimization stuff, which is due tonight, and then this related rate stuff, which will be due next week, is kind of the culmination of all the the derivative stuff we've done. It's like we learned a bunch about derivatives, and now we're going to apply them in these two interesting ways. And so before we do that, we got to learn a little bit about implicit differentiation. And so the word implicit is the confusing thing about that statement, that description. And so let's talk about the difference between implicit versus explicit, right? So if someone says something explicitly to you, they're being very clear about something, right? But if someone implies something or says it implicitly, they're being a little more vague and they're kind of directing you towards it, right? So that's one way to sort of just think about the way those words or what those words means. But with that in mind, in mathematical speaking, an explicit differential or explicit function, like it says right here, very clearly writes the dependent variable on one side of the equation and the independent variable on the other. And so we usually think of the independent and dependent variables as y or f being the dependent, and the independent is the input. And so that's usually x or t. And so it's most equations we've seen and most equations you're familiar with are explicit. For example, let's do a couple examples here. An explicit equation, an explicit polynomial, for example, might be y equals x squared minus 4x plus 6. And that's explicit because the dependent variable y is on one side and the independent variable, in this case x, is on the other side. And they're not mixed up. They're on either side of the equal sign. Or how about some f function? So sometimes you write the dependent variable as f, right? So f of t equals square root of t squared plus 4 or something like that. Right? The f is on one side, the t is on the other side. Or we can do y and t's as well. So how about something like y equals t squared minus 1 over t squared plus 1. Like the thing I'm really trying to point out here in all these examples is we have the y or the f on one side and the x or the t on the other side of the equal sign is what I mean when I say sides. And we've certainly been dealing with these kind of functions so far in this course, because then we differentiate like dy dx or something, and you get y prime on the left, and then you use the rules on the right. And so these are the most of the problems we've seen so far. Just in most math classes in general look like this, but definitely in this course, they've all looked like this so far. Implicit is when you have the variables kind of mixed up on both sides. And so like it says, an implicit function is an equation in which the dependent variable has not been defined in terms of the independent variable, right? So again, we're thinking about the dependent variable as being either y or f of x. And so we might have those mixed up in an equation. So maybe something like this. We have like y cubed plus y squared t minus t cubed y equals 3. And so we're still thinking about the y as being the dependent variable. It depends on the t. But now it's all mixed up, right? We have the y's and the t's are sort of together on one side of the equal sign. Let's write another kind of example. How about Look at the examples I've got written down. How about yt plus t over y equals 6. That's an implicit function. An implicit function we see in pre-calc would be the unit circle, right? X squared plus y squared equals 1. We see that in pre-calculus. That's the equation of the unit circle. And the x is the independent variable, y is still dependent, but they're both on the same side of the equal sign. And so the thing that, sort of the takeaway here, the thing that all these things have in common is that the input, which is either t or x, and the output, which is either y. In this case, I'm just going to stick with y probably. They're on the same side of the equation. And there's nothing we can do about it. Like, that's kind of the key thing too. It's not just that, oh, they're together, but if we could separate them, that would solve the problem. And in some of these problems, and I'm just kind of looking at the ones I chose, trying to remind myself, yeah, all these problems I chose, you can't actually separate them, right? So the input and the output are on the same side of the equation, and you can't isolate them. So we can't explicitly solve for the y. And so there's no getting around it. We have to think about what to do if we want to differentiate this. Let me just pause there and see. This is mostly a notation or like conceptual kind of thing so far. We're obviously going to look at some examples in a second. But do we kind of see the difference between implicit and explicit? Sure. In my first example of explicit, I was using F's and Y's. Moving forward, we're only going to use Y's. And I believe the homework only uses Y's as well. I just wanted to be clear that sometimes we represent outputs with F, and I'll kind of talk about it a little bit in the next step, but you can see all the examples at the bottom only have Y. So we're not going to talk about F really. But the idea is, and what we're about to look at is, even if we can't solve something explicitly, these implicit equations, we still want to think about them in terms of those independent variables. So for what it says down here, I'm about to sort of move into this section and summarize that. It says we can't actually solve for these things explicitly. And so when we differentiate them, we want to think about them as still being functions of t. And then usually use the chain rule. Oftentimes we use the chain rule to differentiate these things. So for example, if we just had like, let me just do a very basic example. Let's say we had y plus t equals t squared or something like that. And let's say we wanted to differentiate that. So let me just do a kind of a mini example right here. So if we did d over dt of both sides, we're still thinking about y as a function of t. And so what happens here is we end up with y prime, or dy dt, plus 1 equals 2t. Right? And so this is the implicit part right here. This is y prime, right? Because y is a function of t. So when we differentiate it with respect to t, it just becomes the derivative. It's like we know there's a t in there somewhere. We don't know exactly what the explicit representation is, and so we're just going to write it as y prime. But the other two things, these were just power rules on t's, right? Because we were doing d over dt. That's sort of the general idea. It's when we differentiate the independent variable, we just use the rules. When we differentiate the dependent variable, we need to use this implicit differentiation idea. Okay, so we're going to look at several examples here, but that's the general idea. Are there questions about what I'm trying to say there? Maybe you want to see an example before you formulate a question, but can I clarify something so far? These are the kind of questions that are in the homework for this week on Wednesday. So there's homework due tonight that was from last week that I've extended, et cetera, et cetera. And then there's homework for Wednesday that's based on this. And these are the instructions usually. It usually says, sorry, I'm pretty sure the instructions, come on, iPad, you can do it. Okay. The instructions say, hey, use implicit differentiation to find the derivative, y prime. Right? But the way you want to think about this is now a notation thing. Let's kind of be clear about this. dy dt, right? This is the derivative with respect to t of y. And so that's how we're thinking about y prime now. And so let's look at this first example here. And I zoom in on this one and kind of slide it over. Great. So it's implicit because we've got t and y on the both on the same side, right? We don't have something that says y equals. And the way we're thinking about this is y is a function of t. And so we're really thinking about this like this. Right? It's like y of t squared. And so if we differentiate this, this is going to end up being a chain rule. Because we're doing d over dt. If we were doing d over dy, it would be a power rule, but we're doing d over dt, and we're assuming y has some t that's hidden in it, like it's a function of y, but we don't know exactly what that explicit function is. And so we're going to implicitly assume it has a t in there and use the chain rule. That's sort of the general setup on this first one. I'm going to try to do this first one pretty slow here, but let me know if I can clarify something as we go. So that's sort of the general setup. And so let's do it. So we're going to do, switch colors here. We're going to do d over dt of the first term. We're going to do d over dt of the second term. And remember, I'm not going to write the of t just to save us some space here. But remembering that y has a t in it. And then we're going to differentiate the 6. And we're thinking about this as a power rule. This one's a chain rule. And this one's a constant rule. And it has to do with the fact that we're doing d over dt, right? So this is where the notation comes in and is important. We're differentiating with respect to t. And so for t squared, just as a power rule. But when we do d over dt of y, y has a t in it that we can't see. And so that's where it becomes a chain rule. We're differentiating a function at that point, right? And then when we do d over dt of 6, that's just a constant rule, and 6 can become 0. Let me just pause here and see if that seems okay so far. So, okay. Let me just do the chain rule part of this over here on the side. We can do the details. I'm going to do the details just one time. So this is a chain rule with the outside function being 3x squared and the inside function being y. And just to be clear, it's y of t. And so f prime is just going to be 6x, but we want f prime with g plugged in, so that's going to be 6 times y. I'm just kind of thinking through the chain rule. I'm just going to write the details down just one time to kind of think about how that works. And then when you differentiate the g part, it just becomes y prime, right? So g prime is just y prime. And so then the full-on chain rule then, if we did like f prime of g times g prime, that's going to be 6y times y prime. And so this ends up being the derivative of the y squared part, the 3y squared part, right? Because we're doing d over dt. And I didn't write that down, but maybe I'll just do this. Recall, we're doing d over dt when we do all these derivatives. And so that's why this turns into a y prime. And so then the next step in the derivative itself, right, we do a power rule, so it just becomes 8t. We just figured out that middle derivative part. That middle part became 6y times y prime, because it's a chain rule. And then the constant just became 0. And so you can see we're going to be able to find an expression for the derivative. We can solve for y prime to get the derivative here. And so let me just pause though, because this is we've done the hard part. We've done kind of the confusing implicit differentiation part.
I have a quick question.
Yep.
How do you know how do you know that y isn't just a variable like t?
So y we're always thinking about in these problems as being the dependent variable, which means we're assuming it's a function of t. So in all of these problems, all the ones on this page, all the ones in the homework, I can just double check the homework too to be sure. There's y's and t's, and y is a function of t. This is how we're always thinking about this right here, this part right here. We're thinking about not just y, but it has a t in there. So when we do d over dt, we need to think of it as a function. And let me just make sure I'm just going to page through a couple of the homework problems. I'm pretty sure they're all y's. There are some x's. There could be y's and x's. I put an x on this one. No, I did y's and t here, but sometimes they're y's and x's. Okay, mostly y's and x's. And so the key thing that we're kind of, when we're looking at this, maybe the original expression, we're doing d over dt on all these things, right? And so d over dt of 4t squared is just a power rule, because it's saying, hey, the variable's t, and look, there's a t squared. How do you do a t squared variable derivative, excuse me, when they're differentiating with respect to t? Oh, that's just a power rule. But this middle term, when you do d over dt of y, that's a different thing, right? And so it's like, whoa, well, how does that match up? Well, if it's a function itself, the way we're thinking about this, it's like there's a t in there somewhere, we just can't see it, and so we're just going to assume there's a t in there and use a chain rule is the way we think about that.
Okay. Thank you.
And we'll see a common thing happening. So basically, anytime the dependent variable like y is being squared or raised to a power, we're going to use the same kind of chain rule idea. Can I look at another one, or can I clarify this one first? I'm going to do the one right below it, which is a little more complicated. And then I'm going to ask you to think about the one on the right, which is very similar to the one we just did here. So hopefully the next one will ramp it up a little bit. Maybe it'll make a little more sense. And then I can think about that other one. Can I clarify something before we do that? Okay, so let's do d over dt of this this next one here. So I'm going to do d over dt, but this is a y of t. And so that's going to end up being a chain rule. I'll write that down in a second. We're going to do the derivative with respect to t of this. That's going to end up being a product rule. And then we're going to do d over dt of this, which is also going to be a product rule. So I'm just kind of thinking about these separately. This one's going to be chain rule. These two are both going to be product rules. Right? Because we're multiplying two things. One of them is a t or a t cubed, and the other one has a t in it. I forgot to write that. So let me make that quick note here. This y is a function of t. And then the last one is just going to be a constant rule because it's just 3. So we're going to get 0. Oh, I forgot to finish the last problem too. I'm sorry. Darn it. Should have finished that last one before I went on to this one and then messed it up. So it's still on that page. So I'm just going to just realize how I had so much room on this last one. I'm going to finish the previous problem. So I apologize if you're still writing this down. Let me just pause and let everyone finish writing that first part down. Because the question on the last problem is, let's find the expression for the derivative. Let's use implicit differentiation to find y prime. And so in that last example, we have y prime in there. So let me just zoom in on this last example. We have y prime, and we can just solve for it. Right? Y prime is currently in that expression. So let's just get it by itself. And then we'll have something that says y prime equals, and that's the derivative. Right? So we can solve for that pretty easily by subtracting the 8t to the other side. 6y times y prime equals minus 8t, right? And then just divide by the 6y. So y prime is minus 8t over 6y. And so that's an expression for the derivative. It's in terms of the function itself, so it's not a typical derivative we're used to seeing. So again, it's implicit, right? We have the t's and the y's mixed up on the same side, but it's an expression for the derivative. And you'll see how this becomes useful once we start using it in on the next page. It's just a different way to approach a problem that's represented implicitly. Sorry about that. Forgot to finish that one off. Is that okay? Or are there questions about how we're starting this next one? I hate to bounce back and forth like that, but okay. So when we take these derivatives with the chain rules, right? So this chain rule right here with the y cubed, and then we're going to have another chain rule inside this product rule. Those two ones are going to be very similar to the chain rule we did on the last one, right? It's a chain rule with like a y that's being raised to a power. And so we're going to think about it as bringing down the power, doing like a power rule, but then multiplying by the derivative on the inside. In other words, it's going to end up looking like this kind of thing. Right, that's how we're thinking about these. And so I'm not going to write all those details. Let me know if you want to see them, or I can talk about them a little more carefully here. But this one, for example, right, this first chain rule becomes 3y squared times y prime. That makes sense. Very similar to the last one, how it was 6y times y prime. Bring down the power, subtract 1 off the power, but then you need to multiply by the derivative of the inside. Right, when we do the first product rule, I'll write out a little bit of the details we're going to do. F prime g plus f g prime. So that's the first product rule. And then the second product rule looks like this. f prime g plus f g prime. And then the constant just goes away, right? It just becomes 0. How's that look? Seems okay.
I think we're
Between the
supposed to
two,
subtract those two.
yeah, between the two product rules, you got to subtract.
Thank you very much. Does everyone see that? This turned into a plus for some reason. It should be a minus. So let me delete that. Thank you. Anything else seem questionable or clarified? And so inside each one of those product rules, then we're going to have another, we have other derivatives to take care of, and they're either a chain rule, so this is another chain rule here, or the power rule. The last one's not either of those things, right? We're just doing d over dt of y. This is just dy dt, which is just y prime. Right? It's not a chain rule. It's just dy dt. So when you have just y raised to the power of 1 and you take d over dt of that, it just becomes y prime. So we get, a similar looking expression that we'll be able to solve for y prime with, right? So this first part didn't change. We do the chain rule on that other piece, and it's going to become 2y y prime, right? d over dt of t just becomes 1. So here's that first product rule kind of repeated. Hopefully that looks okay. And then the second one will become 3t squared times y. And then we just do y prime on the second piece. Let me know how that looks. And we want to solve for y prime. That's the next step, but I want to see if there are any questions here. We're not quite done, right? We want to solve for y prime, but let me see if, this is the important kind of confusing part, right? And if this is a test, you get 90+% of the points for getting this far. And then if we want the expression for y prime, that's how we finish it off. Questions so far, though? So in my notes, I feel like there should be a question. I don't know if people are still writing or not, but does that seem all right?
Yeah, I guess I'm just a little confused. After taking the derivative from the product rules,
Yep.
I guess my question would be, why are we taking derivative of that again on the next step?
So this, if I look at this piece right here, we're trying to take this first derivative of the whole thing, right? And I'm recognizing as this having a t, this being a t, and so we're doing d over dt of two things that have t's in it, right? So that's what makes it a product rule. And so when we do the product rule on this, this becomes this. And now we actually need to do those individual derivatives, right? So the first derivative, it's like, okay, this is going to be a product rule. And then I'm saying, what's the product rule look like? It looks like this. And then when we do that, you need to actually compute these things, right? You need to do like this one and this one. And then we, just like we've done before, it's like, okay, we recognize as a product rule. I'm kind of writing out the details of the product rule and thinking about what do those individual things look like. On the first one, I know y is a function of t, and I'm doing d over dt of it, so that's what makes it a chain rule. And on the second one, if I'm doing d over dt of t, it's just a power rule. And so that's how we're breaking it down. And I'm trying to write out all the details. I don't know, maybe that made it look more confusing. I'm not sure. Does that clarify it?
Yeah, it does. Thank you.
Other things like that? That was a good thing. The last step here is to get y prime by itself, and it's in a bunch of places. And so it's just algebra, quote unquote, just algebra. I know that can be confusing, but that's not like a focus of the course, I guess, is why I would like to make sure this first part looks okay. So I'm going to just do this in 2 steps. I'm going to get everything without a y prime, and I'm going to add it to the other side. And I'm going to keep everything with a y prime on the left. Right, so like 3y squared y prime is going to stay because it's got a y prime. 2y y prime t is going to stay because it's got a y prime. I'm going to move the y squared to the other side. And I'm going to move the 3t squared y as well, because it also doesn't have a y prime. And then this one is going to stay. And so I'm keeping all the y primes together, because now I can factor out a y prime. Feel okay about that? Because now I see there's a y prime, y prime, y prime. So I can factor that out. And then we'll just move it over to the other side to get y prime by itself. Right? And so if we want a solution for y prime, we want an expression for the derivative, that's just what we had on the right divided by this piece on the left that we just factored out. Right, so we just factored these out right here. What do you think? It's all right. This is what's in the homework on Wednesday. There's a bunch of these kind of problems. And I would like to look at some on Wednesday. There's a couple I have in mind in particular, but I would like people to at least have a chance to look at the homework before we do that. For what I'm seeing, no one has started it. Well, one person did a problem. No one else has. So, look at it for Wednesday. Other thoughts about this one? This is a kind of a hard one. This is looking at the homework. This is the level of difficulty that exists in the homework, I would say. Okay. So if there aren't questions, you feel all right trying this last one here? So we're going to do d over dt of this last expression. Right, so we're going to do d over dt of both sides. So it's going to be like this. And there's nothing in those 3 terms that we haven't seen so far. Right, we've got a power rule, chain rule, and a constant rule. And so what we want to try to do here is, so the instructions, Find y prime. Find an expression for dy dt, which is y prime. So do the exact same thing we just did. It's going to be chain rule, power rule, constant rule, right? Just spend a couple minutes, think about that. Kind of compare it to the ones we just did. I don't know if people want me to zoom out so you can see it all. Hopefully you wrote this down yourself, but there it is in case you wanted it all on the screen. And let's just take a second and try that. So I do want to let you finish this one off, but just in case people are a little stuck here, just to get us started, right, we want to do, it's all in the notation, right? So d over dt of t cubed, so that's the variable itself, so that's a power rule. But on the second one, d over dt of y of t, we know that there's some function with the t there, and it's being squared, and so that is a chain rule. And then the last one is the one where we get the constant rule. Just want to do that same kind of thing we've been doing in the last couple. Just gonna wait another minute or so, or if people want to clarify something, let me know. But that's what we're thinking about here. What are the details of the chain while you guys work on that, in case anyone's still confused about that? So that's a chain rule with the outside function being x squared and the inside function being y. All right, so there are the details. Let's finish this thing off. So the power rule in the first one just becomes 3t squared. When we do the chain rule, we'll get 2y prime. Right, that's the thing that we've been seeing a couple times right now, right? This is my f prime with g plugged in. This is my g prime. And then the constant rule to the 4 just goes away, becomes a 0, right? And so this one's not too bad. If we want to get y prime by itself, just divide the 2y over to the other side. And so 3t squared over 2y is y prime. So I've got a little bit of room here. And so let me just finish this one off by doing one that looks like the homework. So a couple of the ones in the homework look like this. it might say, let me look at the way that they phrase it. It specifically says like, find the slope of the curve at some point, at the point, say 1, 2. And so what this is telling you to do is it says, find y prime with the point 1, 2 plugged in. Right? Is it clear that's what it wants us to do? Right? Slope of the curve is the derivative, and at 1, 2 would be the point you plug in. And the difference here is usually we just plugged in like that one variable in, like the x or the t. But now there's a y in the expression, and so we need both those points. Right? This is our t, this is our y. And so this would be then y prime is 3t squared over 2y. We just plug those numbers in, and we'd have 3 times 1 squared over 2 times 2. Right? So 3 over 4, just as an example. Right, so it's taking it a step further and just plugging points in. So there's a couple that kind of look like that. And let's look at that one. So this one has y's and x's, as I mentioned before. So we want to think about this as still y being the dependent variable, i.e. y is a function of x, and x is the dependent variable. I'm sorry, independent. So we want to think about y. This is like y equals something with an x in it, but we don't know what the explicit expression is, right? And so we're going to do, you can see the answer here. We want the answer to be y prime. So we want something that says y prime equals blah, 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 just like we've been doing. And so we're going to take our expression and we're going to do d over dx of it. All right, so we're going to do d over dx of the left side and d over dx of the right side. And so it's going to end up, let me just write out the details here. It looks like this. And this also has a trig, obviously, so hopefully this is a little helpful for that, right? So it's all in the notation, right? So d over dx of sine of x, this is just the sine rule. But when we do it with the cosine part, right, d over dx of cosine of y, that becomes a chain rule. Because you have the y, you have the function inside the cosine. And on the right-hand side, we're going to end up with a product rule, where the individual pieces of the product rule are going to be the same thing as the individual pieces on the left, right? And so let's keep going then. So the sine rule just becomes cosine, or sine is cosine, yes. The chain rule on the middle piece becomes, so cosine turns into minus sine, and then you do the derivative of the inside. Right, that's the chain rule. And then the product rule, how does this look? I have a ton of room. Let me see if I can squeeze it in. So f, it's going to be the individual pieces that we just looked at, right? So f prime g plus f g prime. Apologize, I'm running a little bit out of room there. Let me zoom in a little bit. So that's the product rule. I would describe that as being the hard part of this problem. The rest of it is algebra, which is also, I don't want to say that's not hard, but this is the important part, I would say. This is the implicit differentiation part, the stuff related to calculus. The next part, the algebra part, is still important. And if you want to get this question right in the homework, you need to be able to do that. But it's, if this is a test, I would feel really good if you got this far. Because now we just want to solve for y prime. Questions about the implicit differentiation at all? Okay, there's only a couple minutes left, so I just want to finish this one off. The way we solve for y prime is you want to get the y primes on the same side and get everything else on the other side, right? So this has a y prime in it, and this has a y prime in it, and so we want those to be on the same side so we can factor it out. And the other two things, this and this, are going to be on the other side. So I'm going to show those intermediate steps here, but not all the details. So this will then be, let's see. So how about cosine x minus cosine x cosine y? I'm going to add the thing to the other side, right? So it's going to be sine y times y prime I think that's what I was going for. And then you can factor out the y prime, which is why we did that, right? So factor out the y prime, add it to the other side. Oh, I had more room than I thought. Okay, I don't need that other page. So this side stays the same. I'm going to factor out the y prime. Right. And if we want an expression for y prime, we just divide that stuff to the other side. All right, that's all I've got. I'm happy to stick around and answer some questions. I will put this one into the homework folder. We can look at some more on Wednesday if you want, but I'd like it to be driven by your questions, so you can let me know which ones you want to look at. And let me know what you want to see about this one. Questions about this one? All right, I'm going to hang around if you need anything, but otherwise that is all I've got for today. Thanks, everyone.
Thank you.
Thank you.
I see that question. How'd you go from minus sine to cosine x? Let's see here. I'm thinking, Sebastian, you might be talking about this step right here. Is that what you're talking about? So I grouped the things that were together. So the things that are highlighted in yellow ended up on the same side, and the things that are highlighted in red ended up on the same side. So this went right here. This is right here. And then this is right here. This is right here. And I did that because I'm trying to get the y primes on the same side and things that don't have a y prime on the other side. And so I know it's looking messy, but the point of that was then because you can factor out the y prime, right? So we had a y prime here and a y prime here, and then we factored it out so that we could get it by itself. We want to get it by itself, so we tried to group them. All right, I'm glad that makes more sense.